Welcome to solverfy.
This is the answer to Chapter 15, problem number 55 from the Smith Organic Chemistry textbook. And this problem asks us to consider this bromination reaction of tert butane. And we're asked quite a bit about this reaction. And so for part A, we're asked to calculate the delta H naught by using the bond dissociation energies in table 6.2. Okay, and so I've drawn the reaction out here. So we need to look at what's happening. So this is a CH bond broken. This is a Br-Br bond broken. And so from that table 6.2, to break a CH bond is going to cost 381 kilojoules per mole. To break a bromine-bromine bond is going to cost 192 kilojoules per mole. And so when we add those together, the left side of this reaction is going to require 573 kilojoules per mole. So then looking at the right side of this reaction, these are bonds being formed. So here we have a carbon-bromine bond formed. And so that is going to release 272 kilojoules per mole. And here we have a hydrogen-bromine bond formed. And that is going to release 368 kilojoules per mole. And so our total energy released on the right side is going to be negative 640 kilojoules per mole. And when we add those values together, what we get is that the delta H naught for this reaction is going to be negative 67 kilojoules per mole. Okay, so this is an exothermic reaction. Okay, so negative 67 kilojoules per mole. All right, so that's part A. So for part B, we are asked to draw a stepwise mechanism for the reaction, including all the steps. Okay, so this is a free radical process. And so we're going to start with an initiation step. So that's what the I is for, I for initiation. And so the first thing that's going to happen is that our bromine-bromine bond is going to break when we heat this. And so we will get two bromine radicals. Okay, so there's our initiation step. Propagation is going to be two steps. And so first what will happen is this So the radical here will form a new bond. So after this step, we'll have this. with the radical on the carbon here. And we'll also have some HBr. Okay, and then our second part of the propagation step is going to be the carbon radical that we just formed is going to react with an equivalent of bromine gas, or liquid bromine, as the temperature may dictate. So like this, they'll form a new bond. We'll regenerate a bromine radical here. And so after this step, we get our brominated product. And as I said, we regenerate a bromine radical here. And then lastly, our termination step is going to be when two radicals come together, and after the termination step, there's no more active radical species, and so that is why the reaction terminates. And so that can look like this. So we could have any two radicals in this reaction, but it's nice and clean to say that it's going to be two bromine radicals coming together to reform Br2, and so that terminates the reaction. Okay, and so that is part B of this problem. For part C, we're asked to calculate the delta H naught for each propagation step. Okay, so we have two propagation steps. And so this is going to be, we're going to subtract the bonds formed from the bonds broken. And so for the first propagation step, let's see, we're forming an HBr bond. So let's say F. So formed is going to be HBr, and that is worth negative 368. And again, we're referencing part A for this, or that table 6.2. So formed is going to be negative 368 kilojoules per mole. And broken here in this step, so we'll say B for broken. Broken is going to be a carbon-hydrogen bond. So the CH bond, and that is going to be worth 381 kilojoules per mole. So positive 381 kilojoules per mole. And so we add those two numbers together, and the delta H naught for this step is therefore going to be positive 13 kilojoules per mole. Okay, and we'll just do the exact same thing for the second step. So in the second step, we are forming a carbon-bromine bond, and that is going to be worth negative 272 kilojoules per mole. And we are breaking a bromine-bromine bond. And that is going to be worth positive 192. And so when we add those two numbers together, the delta H naught for our second step is negative 80 kilojoules per mole. And so actually, if you add those two delta H naughts together, you get our negative 67 kilojoules per mole, which is the delta H naught of the entire reaction. Okay, and so lastly, for parts D and E, we're asked to draw the structure of the we're asked to draw an energy diagram for the propagation steps and to draw the structure of the transition state of each propagation step. Okay, so I went ahead and did this because this is already quite a long answer, and this is a pretty time-consuming thing to do. So here's the energy diagram. It's showing how to get from tert butane, we require 13 kilojoules per mole to get to this carbon radical. And then forming the carbon bromine bond is going to release that 80 kilojoules per mole, which we calculated in the previous part of this problem. So there's the energy diagram with transition state 1 and transition state 2 labeled. And then over here on the right, I've drawn the two transition states. So remember, we use dashed lines for bonds that are breaking or forming as part of this transition state. And we use a delta radical symbol to indicate where partial radicals are during this transition state. And so here's TS1 and TS2, and there they are. And again, I just drew them out ahead of time because this is already quite a long answer. So there's parts D and E. Here are parts B and C again. And here is part A. Okay, and that's the answer to chapter 15, problem number 55.